Okay, so let's see. So we should be recording, and I'm going to go ahead and share my screen. Let's do this. All right, give me 1 second here. Okay. Now let me know if anybody cannot see my screen. Okay, so I think we should be good. Okay. So yeah, so pretty much in this session, I'm going to be going over kind of pretty much kind of a review of strength of materials and kind of a review of finite element analysis, FEA, and finite element theory in general. For those who probably maybe took strength of materials a while ago or haven't taken it yet, same for computer aided engineering, CAE. So this will be a good either review or just kind of hitting the high points if you haven't taken them yet of what are kind of the important things you kind of need to kind of know before you start getting into SolidWorks simulation and start running some of these FEA analysis. Okay, so the first thing I want to kind of go over here is these are just kind of basic things with strength of materials. So the first thing, again, for those of you who are taking strength of materials, you're probably very familiar with these, or this might be a little bit of a review. So stress. So what is stress? I'm going to flip my laptop here for some reason. Let me know if anybody can't hear me. So what is stress? So stress is pretty much, simply put, is pretty much the actual internal pressure in a material that actually causes it to fail. So when you're looking at a kind of a misconception that a lot of people have that, aren't engineers or especially, or if they're engineering students before they take, strength of materials or something like that, um, is that, actually you apply a force and the force is actually what, actually fails the material or causes the material to break. And that's actually really not 100% true. So what really happens is the force you apply to a material or to a certain part would do what we call induces a stress in the material. And that stress, which has the same units actually as pressure, so it's usually in PSI or megapascals, will actually it will actually, you have a kind of an internal pressure in the material, and that's what will actually cause the material to fail. So really the force does not actually cause the material to fail directly. That's why, otherwise a force causes the material to fail. If you, hang a 10-pound, weight from, let's say, a little hook that you might use for a coat or something, the hook might break. But if you hang it from, let's say, one of these tower cranes that they use for construction, obviously the crane is probably not going anywhere because it's meant to lift, thousands and thousands of pounds. So obviously it's not really the force that actually is causing it to fail. It's really the stress. So stress, pretty much simply put, is force divided by area. So obviously force divided by area is the same units as pressure. This is usually in, let me see if I can, actually do something here. Give me 1 second. I'm trying to get these meeting controls actually out of the way. Let's see here. Give me 1 second because I just need to make sure these. Floating. Okay, there we go. So let me know if you can't see my screen still. So stress pretty much will have the same units. Sigma is the symbol for stress, Greek letter sigma, lowercase. So it'll have the same units as pressure. So usually you're in PSI in the English system or pascals in the metric system. Sometimes you will actually see people put it as KSI, which is KSI is pretty much a kilopound per square inch or 1,000 PSI if you have a bigger number. And in the metric system, most times you'll actually see people express it as megapascals or 1 million pascals. So again, that is pretty much the internal pressure you can kind of simply put that will actually fail the material. To simply put, if you have, let's say, a kind of a little square rod like this, and you apply a force to it, and it has this cross-sectional area that I have here listed as A. That pretty much, so when you pretty much take the force, you divide it by the area. Let's say the force is 100 pounds, and you divide it by, let's say the cross-sectional area is, let's say, 1 square inch. You'll end up getting a stress of 100 psi. And obviously, materials will have certain, and I'll get into that a little bit more later. Materials are going to have a certain stress that they fail at, which is usually called usually a lot of times you'll hear people call, say, tensile stress or ultimate stress. Tensile stress is obviously for a member in tension, kind of like this one, where you're pulling it apart. You got a force going that way and a force going this way, or it's really one force, but it's pulling it apart. Um, so that's pretty much stress, kind of in a nutshell. Again, what I'm showing here is tensile stress. There are many different types of stress. You have shear stress, like if you were to have a member like this, and you have, let's say it's fixed, kind of it's attached to a wall, and you apply a force like that right at that, very close to the wall. What you're going to end up having, the member is going to end up wanting to do is just kind of shear right off of that wall. So that's a shear stress. It's calculated in the exact same way. So for shear stress, a lot of times you'll see people write, um, you'll see there's, again, sigma equals F over A, or sometimes you'll see sigma equals V over A, capital V, where V is the shear force. So you might see some people write it this way. And this is for shear sometimes. But that's, again, if you have a member kind of like this and you have a force that's applying like that, you're trying to shear it off something. So another really important topic is strain. Again, this is another one of the first things you learn in strength of materials. So strain is pretty much a representation of how much longer, or how much a body has deformed relative to its initial length. Um, so in this case, if we kind of have this member here, what will end up happening? So let's say we're going to call this kind of the same member. You apply this member with those forces, it's obviously going to elongate in some amount. So to calculate the strain, what you'll do is you'll take the initial length, or L, and you'll take the change in length, which is pretty much how much longer the material got, and you'll divide that by the initial length, and it'll give you the strain. So that's a measure of pretty much, sometimes you'll hear people call percent elongation, and that can be kind of derived from strain. Um, Another thing though, so stress and strain are kind of related. Um, um, and I'll kind of go into that maybe a little bit later. But a lot of times when you're designing things or you're trying to analyze, you don't really care about strain as much as you care about displacement. So this is pretty much the same formula. This formula here is pretty much the same as this one, except I just kind of switched L to X. So X is usually what people represent as displacement. So displacement is delta X. So pretty much how much how much has it deformed, pretty much, this body, like here. So when you're kind of looking at the deformation, you're kind of looking at, you don't really care you don't really care about the initial length. You just want to figure out if I have this beam over my head, I don't want it to and I need to have a certain clearance to, let's say, maybe drive a machine or something through. So if I have like a beam, let's say like this, so let's make it a thinner beam. Do something like this. If you have a beam like this, and let's say you put a big weight over it, that beam is going to eventually kind of deflect to something like this. Again, that's kind of, my drawing is not the best. So if you need to, let's say, drive something like underneath here, and you have a certain ceiling height, you may want to know how far this deflects. Because if this deflects like from here to here is, let's say, I don't know, 3 feet, and you have, let's say, 8-foot ceilings or something, you might end up with a clearance issue or something like that. So most times when you're designing stuff, you actually care more about displacement than strain. But again, or displacement can be calculated from strain, and kind of vice versa. So again, displacement, also the symbol for strain is going to be Greek letter, what is it, epsilon. And that's going to be typically what you'll see for strain. Again, this is going to be normal strain, what I'm showing here, but there are other formulas for shear strain as well. But I'm just trying to hit kind of the high topics here. I don't want to completely do an entire strength and materials class here. So pretty much these both go into, actually, before I go any further, does anybody have any questions about stress or strain or displacement? Okay. So these are pretty much related, and in strength and materials, you probably spend a lot of time, or if you haven't taken it, you will spend a lot of time dealing with stress strain diagrams. So this is a stress strain diagram. I kind of like this diagram. It's a little bit simple. I actually found it from this research paper here. So when you're looking at a stress strain diagram, you're actually plotting on a graph the stress versus the strain. So you've got strain on the x-axis, and you have stress on the y-axis. And so what ends up happening is the more stress you apply to material, so as stress increases, obviously the material is going to deform. So it's going to get, like when we're looking up here, it's going to get longer, longer and longer. And the stress will keep going up and up and up until eventually it'll actually fracture. That's when the material will actually break. Um, but a region we're very, very interested in, especially in engineering, is we're really interested in this region right here. I can actually, I'll try to do it like this. This region right here. So this is what's known as the linear elastic region, which means pretty much if you, let's say you have a steel bar, that steel bar, if it's within this region here, pretty much acts as a spring. It acts as a very stiff spring, but it's still pretty much you apply a force, it's going to elongate proportionally to the force applied. So if let's say you apply 100 pounds to a steel bar, and let's say it, I don't know, extends by 1 millimeter, or sorry, not, let me keep the units consistent here, expands by a thousandth of an 1,000th of an inch. If you apply a 200-pound load, it should deform by 2,000ths of an inch. So it's linear. Um, Also in the linear region, that means if let's say you get the stress up to, let's say here, and then you relieve whatever force you're applying, that that displacement will go all the way back to zero. So that you won't really tell that anything has happened to that part. Something actually changes though when you go above this point right here. This is what's called the yield point, this point right here. So that's when a material will actually yield, which means it's permanently deformed. So what'll end up happening is if you get it up to, let's say, I don't know, let's say you put enough stress to, get it up to maybe here, the material will go back some amount, but what'll end up happening is it'll go back like something like this, and it'll end up here. So there's going to be some permanent deformation that you can't really just get rid of by unapplying the force, if that makes sense. Again, all of this is you're probably pretty familiar from strength of materials, but as a good review. So typically in design, you do not want to exceed the yield point. You want to stay below the yield point because you don't want to have a part that's permanently deformed. So you put an axle in a car, and all of a sudden you come back a week later and you find out that it's you take it out, or you can't take it out because now it's permanently deformed inside there or something. So this region is very important for that, especially for simulations, as I'll talk about a little bit later. Um, Mainly because you don't want you don't unless you have a specific application where you're actually trying to permanently deform materials. Like there are some applications like let's say you're in say you're in like some sheet metal industry, or you're in like tube bending where you're bending tubes. Then obviously, yeah, the tube, when after you're done bending the tube, you've plastically deformed that tube. And that's really your desired goal. But once you get above this region, it's going to make your calculations and your simulations a bit harder. So you're not going to be able to just run your, general study anymore. It's going to be, you have to do different things to kind of analyze that properly. Um, Also, an important property that you'll hear of materials is something that's called the Young's modulus, or also sometimes known as the elastic modulus, designated as E. That is actually the slope of the linear elastic region of a material. And this again is for, we're talking about mainly ductile materials here, which means it's a material that will actually extend. It's not just like, it's not brittle, it's not like glass. You apply a force to it and it's not really going to extend much, it's going to break. A ductile material, kind of like a spring, it'll kind of expand out, and then when you take the force off, it's going to kind of come back to its original shape, assuming you haven't exceeded the yield stress. These are all material properties. So the yield point or the yield stress is, again, it's going to be in the units of stress, or PSI or megapascals, and this is a material property for every material, or most materials that are not a nonlinear material, which means a material that will not actually follow a linear path. It might be something that looks more like that or something. Like a lot of polymers and stuff are not linear elastic, so you can't really treat them as a linear elastic material because you're not going to get accurate results. Let me stop there for a second. Does anybody have any questions or have any things that they're kind of would like to ask about stress strain curves or Young's modulus or any type of thing like that? Okay, so that's pretty much a kind of an overview of the stress strain diagram. Again, this is a very simplified stress strain diagram. Usually there is some other stuff going on in this region. You've got the strain hardening region. And usually what will end up happening is if I kind of draw this kind of offset here, if I draw another diagram, usually you'll have the linear elastic region, then it'll kind of go into the plastic region, which is after it's yielded. It might kind of do this. You'll kind of get up to a peak, and then it'll come down, and then it'll fail somewhere over here. And you have some different regions in there. Again, you learn a lot of this in strength of materials or probably in maybe machine design as well. But again, a lot of these things, they're good to know, but they're not 100% necessary to kind of know how to run simulations. Elastic region, though, and making sure the material we're working with is elastic is a big one. If you're trying to analyze a material that's not elastic or has exceeded the yield stress, your results are not going to be accurate. Okay, moving on. So degrees of freedom of a system. Well, actually, I won't say a system. Let's say a rigid body. So typically, if you have, let's say, I can try to sketch out. Well, actually, I'm not going to try to sketch in 3D here, but if you have a body, you've probably heard that there's 6 degrees of freedom, which means that body, I'll just do this, can move in 3 directions. It can move in the, let's see if I can, I do that. It can move in the X direction, it can move in the Y direction, and it can move in the Z direction, which would be kind of in and out of the page if we're looking at it here. So those are the 3 translations. And then you also have 3 rotations, so it can rotate about, in this case, that would be probably the Z axis. It can rotate about the Y axis, and it can also rotate about the X axis. So those are your 6 degrees of freedom. Again, if you have a system that's made up of several links, then each one could potentially have 6 degrees of freedom. Some of them may be restrained, but these are some of the things that you have to look at when you're kind of getting into simulation. One thing I also mentioned here is a lot of the stuff I'm going to start getting into now or in a little bit is I'm talking specifically about SolidWorks simulation. Again, other FEA packages or simulation packages may be slightly different. So don't assume that all of this will apply to another simulation package. Again, most things are like degrees of freedom and stuff are not really simulation specific. That's just more of a physical phenomenon. So any questions about degrees of freedom? Okay. Okay, so fixtures, I'm going to show these are actually 2D fixtures is what I'm actually showing here. But fixtures are going to be very, very important when we get actually into simulation. We start looking at different things. So these are going to be 2D fixtures. So most common 3 types of fixtures, you have a fixed constraint, which is that. So it's usually you'll see a plate or something like that. You've got a member that's going into that, and you see those little lines saying that it's fixed. So fixed constraints or limits all degrees of freedom. So this cannot rotate. It cannot so it cannot rotate this way. There's no moment. Again, a moment from statics, a moment is equal to a force times a distance. So it has the same units as torque. So if you have, let's say, an arm you have rotating around this point, and you apply a force F, the distance here would be d. Kind of just a review from statics. Again, most of you probably already know this, but for some of the people that are either here or are going to be watching the recording of this that have not taken statics or haven't taken strength of materials, and this will be a bit of a kind of overview of kind of some simple things that will help. So for 2D, the fixed constraint is going to limit all degrees of freedom. In that case, you're limiting a moment. That moment there, you're limiting translation in the X direction. You're also limiting translation in the Y direction for 2D. For 3D, you're limiting all 3 translations, X, Y, and Z, and all 3 rotations. Rotation about X, rotation about Y, rotation about Z, or moment about X, moment about Y, and moment about Z. Again, it's going to be a little bit tricky for me to actually show 3D here, but when we get into SolidWorks simulation, probably the next session, I'll show exactly kind of what we're looking at in 3D, because obviously most of the things we're going to be analyzing is going to be, or is actually going to be, let me actually leave those there, is actually going to be useful when we're looking at 3D systems. So the next one is going to be a pin constraint, which is going to be this one here. That's genuinely or usually shown with usually kind of a triangle shape like that. Sometimes you'll see it kind of have this, looks like it's fixed on the bottom, but really the constraint we're actually looking at is the pin. So if you kind of think of, if you have, let's say, I don't know, you have like a member, if I can actually draw here. you remember, again, my drawing is not the best, but if you remember like this, and you have a pin maybe going through this hole here, this member can't obviously go up. It can't move along the X or along the Y. It can only rotate about that pin. And this again is in 2D, and 3D is similar. So yeah, this is going to limit the two translations. So this piece here, it cannot move in the X, and it cannot also move in the Y because it's a pin, and that's how you would show that. Again, this is you'll see that a lot in strength of materials and statics. Um, a roller constraint will limit one translation. So a roller, think of you have like a think about you having a wheel that's on the ground. So obviously, whatever is on the wheel or whatever is supported by the wheel is not going to be able to go into the ground. So it's preventing this member from hitting the ground. So there's in this case there'd be no translation in the X. Sorry, not the X, the Y. But obviously it's free to move in the X, and it's also free to rotate. So the moment here is also unrestrained. Again, those are the simple ones. Again, in simulation, we'll go most of, I would say pretty much all of the fixtures that we're going to be dealing with are going to be 3D fixtures or some variety of them. So yes, I'll definitely talk about that more later. Okay, so any questions about fixtures before I get into what is finite element analysis? Okay, perfect. Okay, so what is FEA? What is finite element analysis? Some of these, this is actually the book here that is usually used in when they teach CAE. I might have an older version of it, but this is where I'm getting some of these images. Um, but so pretty much what is FEA? FEA is pretty much a way of actually predicting the behavior of a part or assembly or some sort of system. So what FEA pretty much entails is what you're going to do is you're going to break apart like this one into a finite number of elements, which are all of these little elements here. And you can a lot of times have thousands of these or hundreds of thousands of them. Um, sometimes even millions, depending on what you're looking at. And pretty much what you'll do, again, this is a very simplified explanation. Again, you could spend probably, entire semesters just talking about how FEA works. Pretty much what you'll do is you do an analysis pretty much on every single one of these elements. Or obviously, you could do this by hand. Again, this would take forever. So more people will, or most engineers these days are going to do this on the computer, because nobody wants to sit there and, literally, compute 1,000, doing a statics problem on a, 1,000 element system or a 10,000 element system. Again, it is possible, but nobody, again, somebody would kind of be crazy to try to do that. So pretty much what you'll do is it's going to analyze the forces. It's going to analyze how each one of these is deforming. How is it moving? How is it deflecting? And when it figures that out about all these different elements, also another thing. So the elements, and I'll get into elements. Elements, these are what's called solid elements. This is a shape that's called a tetrahedron. So it's like a three-dimensional it's like a triangular pyramid. So it's like a triangle. And again, if I could, I'll scroll. Actually, I'll talk about elements, whereas I've got a little picture down below about elements. So those are called elements. They're actually a three-dimensional solid shape. Um, and then when you have between elements, you have what are called nodes. So these points right here are called what are called nodes. So each element will have a different amount of nodes. Solid elements, I'll talk about that when I get into nodes. But pretty much what FEA does is it's going to analyze every element. How is it deforming? How is it doing this under the parameters you specify? If you apply a force, if you apply something. And based on that, when it computes all of the behavior of all these different elements, it can give you a picture of the part, something like this, and it can actually predict, or it can say, you might have an area of high stress in this area, or you might, let's say if you want to figure out your displacement or your deformation, how much does, this face here deform? So it can be very, very useful when you're designing parts to make sure before you actually have to go and make a prototype of the part and say, hey, I need to go machine machine a prototype of this part I'm trying to design, then put it on an actual physical testing machine and actually, test it and say, I want to apply, 100 pounds of force. Will this break? How much does this deform? This is a way that you can do all of this on the computer, and it's a way that saves quite a bit of time and also quite a bit of money and resources when you're developing products. And and parts where you can kind of get an idea. You can do a lot of it. You can do a lot more iterations this way because you can modify something and then quickly run a simulation based on that modification versus having to physically go and machine a part every time. The cost can be very, very high. We're doing it that way. You'll also hear some people call this. So obviously, you're probably all familiar with the term CAD, computer aided design. Um, Usually, what will happen, CAD will go to what's called CAE. All right, CAE, which is known for, which means computer aided engineering, which is pretty much analysis like this, FEA type of stuff like that. And then what will end up usually happening is then after that, when you want to actually fabricate your part, you'll put your thing in what's called CAM, computer aided manufacturing. Again, for mechanical engineers, depending where you're working, you may or may not have to deal with CAM at all. They don't teach that in the mechanical engineering degree. METs do teach CAM because they do a lot of machining work and stuff. But yeah, so that's kind of the process you're going to go through. And typically, what will happen in the design process is it's usually going to go from CAD to CAE, then it may go back to CAD. You make a modification, then it goes back to CAE, or simulation in this case, or pretty much simulation, and then you're going to keep going round and round until you actually get a um, part that you're actually happy with. You can change the material, make sure you have the right material, make sure you're getting the stress you want, and stuff like that. Um, any questions about FEA in general or anything I've just talked about? Okay. Okay, so next I'm going to talk a little bit about elements. So there are different types of elements. These that we looked at earlier are what are called solid elements. So a solid element looks something like this. So it's what's called a tetrahedron. So it has four faces. It has one face, two faces, three faces in the back, and then it has a face at the bottom. So it's pretty much a triangular pyramid with a triangular base. Um, so that's usually used for solid for parts that are relatively thick, kind of like this. You can see that you can fit quite a few elements in there. There are also something that's called shell elements, which are it's kind of a 2D element. It's technically still 3D because it can deflect in 3 dimensions. But geometrically wise, when you start out, it is just a triangle. So typically what that'll do is if you have like a very thin part, like something like this, and you're applying, let's say, maybe you have like a thin sheet metal something, and you're applying a force. What you can do is you can actually approximate, what's the word? You can treat this as a shell, and you can actually have all these little triangles, kind of treat all of the sides as little triangles instead of solid elements. The reason for this is a lot of times the more elements you have in a model will dramatically increase the time it takes to actually run the analysis. So we definitely want, so shell elements typically is a way to kind of simplify. It may not be as accurate as a very, very fine solid element, but it saves a lot of time, and usually the accuracy is close enough for most applications. So it's worth having the time savings and also the computational resource savings to not have to be running a simulation for, I don't know, 10 hours to get an answer that's within, I don't know, 5% or 3% of when you're using shell elements, and it might take, I don't know, an hour. Again, those numbers are just off the top of my head. Again, it depends on the part, depends on a lot of different factors. Um, Another type of element is what's known as beam elements. So something like this. Beam element is pretty much when you have a beam that has a constant cross section, kind of like this I-beam. What you can actually do is a beam element is kind of, again, in research here, we're probably not gonna, we may or may not use beam elements. I'm thinking we probably won't. But if we do, I can definitely go into more depth on those at a later date. But pretty much a beam element is treated kind of like a line. And you have usually a node on each end, and in some cases also a node in the middle, depending on on the order of the element and stuff like that. So when you're dealing with beam elements, it's kind of like calculating forces on a line, and then simulation will actually go back in and actually treat kind of do the I-beam cross section after the fact kind of thing. I wouldn't say after the fact; it's all part of the analysis, but you don't really see the actual cross section, but it is accounted for in simulation. So it's another way to kind of simplify instead of having to use a ton of solid elements with a very, very fine, like do very, very fine elements or a lot of them. When you have a constant cross section, a beam element is another way to kind of simplify elements, or kind of simplify the number of elements and simplify the calculations that you need to do. There are 2D elements as well. You can also run just 2D simulations, which are a lot more simple than 3D. Again, typically, these are usually in very specific cases where you only maybe have forces in two directions, versus if you have a component or a structure that's deforming in three different directions or in 3D. So again, we probably won't deal with a lot of this either, but just so you kind of know that it exists. So another thing, so one thing in SolidWorks that this is something you do definitely want to know. There is a distinction between first order elements and second order elements. Pretty much what that means is for solid elements, a first order element obviously has a node at each. Ooh, I zoomed in way too far there. Has a node at each corner. So node here, node here, node here. So there, there, and there. So you node at each corner. So a regular tetrahedral solid element will have 4 nodes, one at each corner, or what I guess if you could call those corners. What will happen if you go to a second order element? It's still a tetrahedral element, but you actually have, not only do you have 4. Let me actually switch to red so it's a little bit easier to see. Not only do you have 4 nodes, one at each corner, you also have a node in the middle of each segment. So what this allows the model to actually do is not only you can not only now just figure out the displacement and different properties of each corner. This line here can also now deflect, and you can actually displacement. You'll end up with a parabolic kind of displacement. This is a lot more accurate than this. In SolidWorks specifically, you will not sometimes see you won't actually see the term first order and second order element. What you will see is something that's called draft quality. So draft quality is designating a first order element, and high quality is designating a second order element. Typically, you always want to use second order elements. You don't want to use first order elements unless you're just trying. The kind of the exception to that is, let's say you want to just you put all your fixtures, you put all your forces. Again, I'll get into all this later, and you're just trying to figure out how the actual body behaves. So let's say you've got a rod. Let me actually try to let me scroll up here. Let's say you maybe have a rod in tension or something. Let's say it's fixed on this face, and you're pulling on it there. And you want to just kind of see, does this actually behave the way I think? Obviously, this should extend. It should end up extending something like that. So draft quality is good for that. You don't really care what the results are. You're just trying to actually see, is the deformation, is the behavior of this model actually what I'm expecting? So sometimes you can do a draft quality because it saves time to just see, okay, am I getting the behavior I'm expecting? If you are, then you can go back and switch it to a high quality. If you're not, then you have to go back and kind of look at your fixtures and forces and everything to kind of make sure that everything is set up properly, or you might have to change some things. But yeah, when you're doing calculations or doing simulations, you definitely, I'm not talking like just checking your setup, you definitely want to use high quality or second order elements. Similar thing here for shell elements, a node at each corner. This one, again, you have a node at each corner and a node at the midpoint of each. I'll call them, I would call them lines, but these can actually deflect into it's a parabolic deflection. Again, similar things with 2D elements. Some of this kind of also applies to beam elements and 2D elements as well. Any questions on anything about elements or anything? Okay. So again, a lot of this stuff you won't actually necessarily see when you're in simulation, but you obviously knowing what you're dealing with, because if you're running all of your things as draft quality, your results are not going to probably be that accurate, although it's not it's actually not, you won't really be able to tell that unless you actually just kind of look at that. And then all of a sudden, maybe somebody else runs a simulation, they're getting very, very different values from what you're getting, or maybe not very different, but they're enough different that there's, cause for concern. That is definitely something. So these are the kind of things you kind of want to have in the back of your head while you're actually setting up and running simulations. I will talk here a little bit about kind of the difference. Again, all of you may be probably are familiar with CAD and some things. You may or may not be familiar with SolidWorks. But CAD, it typically functions similarly between packages. Typically, when you design a part, it really, as long as you kind of get the desired thing, you get the right shape, you get the right sizes or right dimensions, and you kind of, that's pretty much all you really care about. You want to make sure, the part is the right shape, the right size. That's pretty much that's good. That's pretty much your goal in CAD is just to, when you're designing something, you want to get a design that, looks at what it like pretty much looks like and is what you want it. So for simulation, or FEA in general, it's not as straightforward as that. So put it this way, when you're designing a part, you really don't necessarily care exactly how SolidWorks is actually, when you do a revolve feature, you don't really care about, the calculus and all the math and everything that goes in behind there. Some people do, and it's great to know how it works. But beyond, just kind of a curiosity thing, it really doesn't impact your job at all as a designer to kind of look at, yeah, it's using, this partial differential equation, or it's using this topic from, I don't know, calculus 3 or 4 or 5 or whatever. So that's a bit different from simulation. So when you start getting into simulation, you you don't necessarily care exactly the formula that it, well, I'll take that back. You do actually kind of care, but you really do care about exactly how it's calculating it. Again, you don't have to go into and actually do every calculation for it or check every calculation. I'm not saying do that, because that again, it would defeat the whole purpose. But what you do care about is you want to make sure simulation, very simply put, is a very, very advanced calculator. You put a set of inputs in and you say, this is what I have. Like, for example, you're going to put a material. You're going to put you're going to put some fixtures. You're going to put some, loads. I wanted this amount of force and I have this geometry that I'm dealing with. And you're going to put that in and you're going to have it run with a certain mesh. And it's going to give you a result. It's usually it'll have a plot that looks something similar like this. I'm going to have some examples at the end. So you can kind of see exactly what the interface in SolidWorks actually looks like, because it is like this, but it looks a little bit different. This is more of a simplified version. And it's going to give you this nice, pretty picture. You've got all the colors, you've got all this stuff. The thing is, and this is the tricky part of simulation, pretty much every time, unless your simulation just errors out for some reason, which can happen, but that's usually because you just didn't set it up right or something, which at least then there's a problem. A lot of times you'll get this, and the engineering part of this is making sure that this picture it gives you is actually representative of what you're actually dealing with in real life. Because just because this picture on the computer, it's this nice pretty picture, does not really necessarily mean that the actual part you're actually dealing with is actually even set up correctly. You might have different fixtures, you might have different whatever in real life. Although you put it in SolidWorks a certain way, and it's going to give you the output. So it's pretty much like on an exam. You put your long formula into your calculator, and I don't know, you forget you do, like, instead of putting in 355x, you put in 55x. Obviously your answer is not going to be anywhere close to what the actual correct answer is. So that's where with simulation, that's why it's very, very important to actually know at least a basic understanding of what kind of happens on the back end of simulation, kind of what elements are, kind of different things like that. That's a lot more important than when you're just dealing with CAD, where if you get the part you want, it's got the right, right shape and everything, you're kind of happy. With simulation, you not only want it to, look nice and, obviously, have the correct parameters, but you also want to make sure that the results you're getting out of it are actually accurate, because that's literally the whole point of simulation, is to actually, kind of predict real life behavior of parts. So if you're not getting an accurate prediction, simulation is really not helping you very much. One thing I will talk about with elements, so solid elements, so if you're looking kind of here, if you're kind of looking along here, when you look at a thing, you can see one thing you'll look at is how many elements are across. So across the thickness, some people will call this. So if you kind of look here, there's actually 3 elements. There's 1, I'll try to put these in different colors. There's 2, and there's 3. There's 3 different elements across. For solid elements, you typically a minimum, you typically want at least 2 elements across the thickness. Ideally, you usually want 4 to 5 if you can. So again, element size is, you can obviously, if you need more elements across, you can shrink the element size. Again, what will end up happening is that's going to make a lot more elements. It's going to make your simulation longer. But again, you do want to have a reasonably accurate simulation. Another method sometimes you'll see people use, and again, this is I'm a little bit off topic here, but you'll see people use is they'll run a simulation with a more of a coarse mesh, so maybe something like this, and then they'll run another one with a very, very fine mesh, so with a lot more elements. So they're trying to get an idea of, something coarse, run something quick. Are we even in the ballpark, or is this part just going to automatically fail? And then if they're kind of getting numbers that look, like they're happy with, then they'll run something a lot finer and say, okay, let's really, really look at this and see, let's get a much higher level of accuracy. Because again, the more elements you have generally is going to mean you're going to get a lot more accurate prediction, because you have, especially when you're dealing with regions that are curved like that. You can kind of see here some mesh types will actually, or there are different types, there are different ways to mesh in SolidWorks, not just elements. There are some things that are called like curvature-based meshes. And when you have a curved surface, it'll try to make a finer mesh on that surface, or along that curve or that fillet. So definitely, when you have features that are changing rapidly or something, you definitely want to try to get a finer mesh in there. Any questions about anything so far? Okay. So moving on. So failure theories. So if you've taken what is it called? Machine design. You probably be familiar with at least a couple of these. Again, it's not really important to know exactly how these are calculated. Again, you can look these up, and there are formulas of how these are all calculated. So SolidWorks predominantly is going to use the four default, or not want to say default, but the ones that SolidWorks will use, failure theories are these four. You've got distortion energy theory, you have maximum shear stress theory, you have Moore Coulomb failure criterion, and you have maximum normal stress theory. This is actually should be an N. That is a typo on my side. Let me see if I can fix that. Again, sometimes you'll see different abbreviations as well. And of course, that should be N S MNST. So typically, again, for anyone who's taking machine design, you're probably familiar with probably these two, especially, or if you're a grad student and you've taken applied engineering design, I think is what the class is called. Um, you probably are familiar with these two, DET and MSST. DET is the same thing as saying von Mises stress. So in SolidWorks, a lot of times you'll see von Mises stress that is using DET. So that's kind of the more common term for it. These two here are meant for ductile materials, while the Moore Coulomb and the maximum normal stress are for brittle materials. So different materials, like, if you're dealing with like glass or something like that, that's not really a ductile material. It's not, they're really, and what I mean by ductile versus brittle, when you're dealing with a ductile material, obviously, like we were talking about earlier, when you have, let me actually switch colors here. When you have a stress strain curve, and you're gonna have that linear elastic portion, and then you're gonna have a yield point, and then it'll do whatever else. Um, a ductile material is gonna have a designated yield point. So there's a point where it'll yield. Um, Brittle materials, they don't really have a yield point. They just pretty much, they'll get to a certain point and then they'll just break. So it's not really, it's not a it's kind of a slow failure. It's going to just like a bolt. Some bolts they're very, very hardened. So they're very strong, but they're not really going to give any warning before they go. They're just going to pop. So brittle materials and ductile materials behave in different ways. Ductile materials are more, they can, lengthen and then, come back. You can extend them and bring them back within reason. Um, Again, these are, it's just kind of something to keep in the back of your mind when you're doing simulations, kind of when you're looking at different materials and stuff like that. You kind of want to kind of figure out, make sure you're using the right failure theory. Again, most of the time, von Mises is what is used, because the majority of stuff that's being simulated is going to be, with is going to be ductile materials, and you're talking steels and stuff like that. Um, any questions or anything about failure theories or anything else? And everybody can still hear me, right? I think so. Yeah. Okay. I think everybody's here. Okay.
Yep.
Yeah. Okay. Perfect. Just want to make sure. Okay. Okay. So next, assumptions. So what I'm going to start talking about mainly is in SolidWorks, there are different types of studies you can run in SolidWorks. A study is just pretty much a setup, is pretty much the simulation we're running. First and most common is going to be a SolidWorks static study. So pretty much from statics, you don't have any motion and stuff like that. And I'm going to go through these assumptions because these are actually very important. This is something that actually wasn't really taught in my CAE class. Again, maybe different professors teach different things, but this is actually some of the stuff you do need to know for the associate certification, CSWA-S for simulation, kind of the assumptions. So pretty much, obviously, before I go into the assumption for a static study, you pretty much have two you kind of have two general categories for studies. You have, obviously static on one end, and you have dynamic on the other. So pretty much from statics, or if anybody's saying dynamics, static, it's static. The structure is not moving. You can pretty much assume that you can also sum all forces to be equal to zero. So in statics, the big equation that a lot of people use is sigma. Oops, I can do that. My computer doesn't act up. Okay, let me put that off the side. The big equation that sigma f is equal to zero, and also sigma m, sum of moments, is equal to zero. So those are the big two for static. Um, that assumption. Dynamic, obviously, it's not necessarily true that all the sum of forces is equal to zero. Sum of moments, the structure may be moving. It might be like a car. So the forces may not necessarily sum to zero. Um, and then a subcategory under there, these are the main ones. You have under static and under dynamic, you have, I'm actually going to move this out here so I stop clicking on this text box. Under static and dynamic, you have what's called linear. You have a linear study, and you have a nonlinear study. Same for dynamic. So this is also the same here. So pretty much, what does linear mean? We talked about this a little bit earlier. Linear means that you are, when you go to your stress strain curve, I go scroll back up here, you are again within that region here. You're assuming that the material is elastic and it's behaving linearly. Um, that is a big assumption. If you're dealing with a material that's not linear, or you're dealing with a material that is linear, or it is a linear elastic material but has exceeded yield strength, then that is now behaving non-linearly. So you can't just assume that you apply double the force, you're going to have double the displacement. It's that assumption is no longer correct. Same thing happens for dynamic. So again, nonlinear does add an extra level of complexity. And I will mention a little bit, there are different levels of SolidWorks simulation. The first one is just SolidWorks simulation. This is the standard one. The standard one that usually just does static studies. And when I mean static, I'm not talking nonlinear, just regular static linear studies. Then you can go up to SolidWorks Simulation Professional, which will have you might have some thermal stuff, and then you probably have a bit of dynamic simulations. And then you have SolidWorks Simulation Premium, which again, this is an overview, but you can actually go online and actually see all the comparison between the three. And then you'll end up with nonlinear type things. You'll have nonlinear dynamic, nonlinear static. So especially if you're in the workplace, simulation can be very pricey, especially simulation premium. It runs as quite a bit of money. So a lot of times people don't necessarily need premium if they're only running static studies for linear materials. So that is one thing to kind of keep in mind. Obviously, for students, with our student edition, we have pretty much simulation premium, the student version of it. So we have the ability to run static, dynamic, or nonlinear of any variety, as well as thermal and a whole bunch of other stuff. But for static, so what I'm gonna focus on now is static. This is the most simple case. Then at some point, obviously not in this lesson, probably once we get a good grasp on static simulations, then we'll probably go into some non-linear, or not, sorry, not linear, some dynamic. Because for the FED project, fluid viscous dampers, if you're dealing with vibration, if you're dealing with something like that, that's going to most likely go into a dynamic simulation. Okay, so for a static study, so what are the four assumptions? The first assumption is it's a linear elastic material. That is a big one. Obviously, like I said earlier, if it's not linear elastic, or like I said, if it is a linear elastic material, but it's not in it's not in the linear region of the stress strain curve, then you're not going to be able to obviously you can still simulate it, but your results are not going to be very accurate. Um, let me see here. Okay, so one person needs to leave. Yeah, you're good to leave. Yeah. And again, this will all be recorded as well. That's for a later review because I know I am going through quite a bit of material. There's kind of a lot to unpack, and this is again just kind of the highlights of the stuff you need to know. Another big one, and this is most times you will be taught this in CAE, linear elastic material. Obviously, if you're doing that, it has to be linear elastic material. Another one that not necessarily is as what's the word? Well, I guess maybe not. I don't want to say necessarily well taught, but not taught as much is small displacements. So what I mean by the small displacements relative to the size of the model. So let's say if you have, if you have a huge, I don't know, you have this huge I-beam, like this or whatever, it's an I-beam, and you apply your force and it's, it deflects, I don't know, 0.0001 millimeters or something that and this is like an I-beam that supports a bridge or something. This is some huge, really long I-beam. That displacement relative to the size of the model is very, very small. So that's another assumption. If you have, let's say, I don't know, you have this tiny little pin. Let's see if I can draw this. You have this tiny little pin, let's say, that's put in some sort of hole or something, and you apply your forces or whatever, and assuming, let's say it even stays linear, it doesn't actually permanently deform or anything, but this little pin is, let's say it's, I don't know, if, let's say it's, again, I don't know what material it is. Let's say it's 1 inch long. Let's do it that way. 1 inch long. That is inches. Yeah, 1 inch long. And this thing deflects, you have a force there or whatever, and that thing deflects like, I don't know. Let's assume it stays linear. Again, these are numbers are kind of not this are realistic. Let's say it deforms 1/4 of an inch. So now you have a pin and now it's like that type of thing. And there are certain what is it called? There are certain values. The thing typically for this one, SolidWorks simulation will actually tell you, it'll actually give you a warning if it thinks that your displacements are too large relative to the model. But that is one. A lot of times people get that message. We're detecting large displacements. Are you, is this? Do you want to run it? Because there is a thing in SolidWorks simulation. You can do this in a static study. Is to treat it. You can use a large displacement model versus a displacement model that's meant more for small displacements. So this is something if you have really, really large displacements, the model for small displacements is not going to be it's not going to be as accurate because it's obviously built for, when you have very, very small displacements relative to the size of the model. So again, it's relative to the size of the model. So you might have I don't know, you have a 150-foot long beam, and let's say you put it under tension, or let's say another beam, a 150-foot long member, and you put under tension and it extends 1/4 of an inch. Obviously, 1/4 of an inch on 150 feet is not the same as 1/4 of an inch on a 1 inch long segment. So hopefully that makes sense. Another thing, loads are applied slowly is the third one. So loads are applied slowly, meaning you don't want to simulate, this is not really for simulating impact with something. You're not going to do a car crash. Again, usually if you have loads that are applied very quickly, depending on the magnitude of the loads, this can also go nonlinear as well, because if it's obviously like a car crash, the car is obviously the bumper, a lot of stuff is on it is going to be permanently deformed. So then not only is it, the loads are not applied slowly, but you're right into a nonlinear analysis. So kind of like in statics, you're assuming that the loads are applied very slowly. it's under this, load. It's, you don't really have to worry about, the load. All of a sudden it's like somebody throwing a bowling ball onto a glass table or something. Or because yeah, obviously, or like even not a glass table, a plastic table or something. Then in that case, so if you have a load that's applied, if you've got a scenario where a load is applied quickly, even if you know what the load is, that is you're kind of getting into kind of a gray area of a static study, or getting into the point where it may not be extremely accurate because of that fact. Another thing, for fourth assumption, inertia effects are negligible. This pretty much goes to statics. Um, like the structure is not, the whole thing is not moving. So you don't have the whole structure is not moving. This is not a car in motion where now you're going around a curve, or a turn, and now you have all these, inertial effects that you have to deal with. It's a structure, it's a part, it's being held, it's static, it's not really moving. So that's pretty much where kind of where the what's the word? Yeah, it's pretty much the same kind of assumptions from statics, but just kind of put in a little bit of different way. Um, yeah, any questions on assumptions, or different types of studies? Okay, so I'm now going to get into an example, and I'm going to kind of from now on, I'm going to kind of go back and forth with you all, and I'm going to kind of explain. This is kind of generally what your study is going to kind of look like, in solid simulation. But I'm going to start kind of asking you kind of for feedback and different things, and seeing, kind of a little bit, kind of testing you on, like, kind of based on what I've talked about, are these results accurate, or can we expect them to be accurate, type of thing. So here's a part. This is just a quick part I whipped up in SolidWorks. The material is plain carbon steel. And pretty much what happens is I'm applying a force, little green, or sorry, not little green, little purple arrows, um, in SolidWorks simulation, designates a force or a load. Again, all these colors can be customized, but this is the default, and this is what most people use. Green, these little green things here are done for fixtures. So pretty much what happens, this entire back face, from the backside, is completely fixed. So it's 0 degrees of freedom, and there's a load applied to this face. I'll actually do it here. There's a load applied to that face right there in the down direction. I believe it's 1,000. I want to say it's 1,000 Newton load. I think this is 1,000 newtons. And then the back face here, obviously, this entire face back here is fixed. Okay, so you have that's fixed. When you're going to do that, again, I'll get into kind of the process once probably we get into SolidWorks. Probably the next session, because I'm kind of coming up on about an hour, and I don't want to hold you guys up too long. So you're gonna, once you apply everything, you set it up. Again, I'm not gonna go into the setup right now. Once I get into SolidWorks, it'll probably make a lot more sense. You're gonna get a result. This is kind of what you would expect from a results plot. This is a stress plot. Obviously, it's in von Mises stress. It tells you the units, newtons per millimeter squared, which is megapascals. It's also obviously so megapascals. So based on everything, and again, if anybody hasn't, let's see. So you guys tell me, do you think are these accurate results? Yes or no? And if anybody hasn't taken strength of materials yet, I'll let them answer first, because I'm curious. Or sorry, strength of materials, or CAE for that matter. If anybody hasn't taken either one of those, and then I'll kind of open it up to everybody. So do you think this is these results are accurate? Yes or no? And if so, or if not, why?
Um, I took CAE like 8 years ago,
Okay,
but I would right now I forgot a lot. But
you're
looking
good.
at this simulation, I would say yes, it's fairly accurate.
Okay.
With von Mises, of course, with simulation, it can only do so much. But I don't know what kind of, is it tetrahedral or linear shapes that you're using. But I
These are
guess
yeah, these are tetrahedral solid elements. I should have mentioned that. Yeah.
Okay, yeah. Well, the more fine it is, the more accurate it will be. But yeah, for this case, it's fairly accurate. It looks like just angle iron with like a load on the end of it. So
Right. Okay. Okay. And then anybody else? Anybody think it's not correct? Let's go there. There's got to be somebody who doesn't think it's correct, right? Maybe. Okay, so everybody thinks it's correct. Okay. Yes. So the answer is yes, this is actually correct. For a couple of reasons. One thing I'm going to look here is, yeah, obviously these are solid elements. I should have mentioned that before. Um, Again, you can usually tell from the plot as well if it's solid elements or not. If you can tell if they're shell elements because a lot of times you'll see it's going to be like a thin shell type deal. Things I look for when you're looking at a simulation. The first thing is obviously this is a static study. I should have mentioned that as well, but obviously you can tell based on it being fixed that it's static. The yield strength is 220 megapascals, 220 and change. The maximum stress is 101.195, which means this material, it's got about a factor of safety of 2. Again, I can talk about, so factor of safety is pretty much um, like it's pretty much how much more capacity you have out of a part. It's pretty much it's the it is how do I put this? It's pretty much what you do is it's the yield stress. So factor of safety or FOS, which is what most people say. FOS is equal to the sigma. In most cases, it's going to be I'm going to put failure because it depends on what you're trying to do. The failure stress over the actual stress. So in this case, the failure stress, in this case, we're going to, in most design applications, the failure stress is going to be the yield strength. Most people don't want their part just to break. They're going to treat yield, because usually, if you remember the stress strain curve, there's usually quite a bit of room after the yield before, if you're dealing with the ductile material, before it breaks. So yield, typically, all of your factors of safety are based against, or you're designed against yield, not against ultimate. You just don't want the thing to break on somebody's head. So obviously you'd want to design against yield. So in this case, it's the yield. So in this case, you're going to have a yield strength of, let's say, 220. Oh, sorry, oopsies. You have a yield strength of 220, and you're going to have a failure. Actually, I actually reversed that, didn't I? Oh, sorry. No, I did not. Failure, yeah, I actually had it right the first time. You've got failure of 220 megapascals. And I'm going to try to wrap up here probably in the next 5 or 10 minutes because I don't want to keep you guys too long. 220, and then you have an actual of, say, 101. So that's pretty much when you do that, you're gonna have a factor of safety of over 2, which means you can apply pretty much double the load, actually more than double the load in this case, and before the actual thing will break or fail in this case in yield. So yeah, so in this case, this has not gone into if it's exceeded the yield, then it's nonlinear, but that's not has not occurred in this case. So this is why this would be a correct this would be a correct result, or this would be a correct result. Um, Another question. So let's say we have the exact same part, exact same loading, exact same everything else, but instead of plain carbon steel, we have instead gray cast iron. What do y'all think? With these results, and let's say the load might change. Let's say these are the same exact results, though. Let's just say hypothetically. Anybody?
I would think that it's inaccurate
Okay,
because
why?
of how much more brittle it is. It's
Yeah,
not, yeah, based on your failure theories that you showed previously.
right. Very, very good. So yeah, that is something to check. So the thing is, yeah, typically for SolidWorks, when you're dealing with materials, it will typically have a default failure theory. If it knows it's a brittle material or if it knows it's a ductile material. So it typically will pick the right failure theory. The thing where you can run into issues is, let's say you're doing a simulation and the material you're trying to use is maybe not one of the default materials in SolidWorks. So you go to a website and you find the material properties. A really good website is called MatWeb. I think you can, I believe it's free. You might have set up like a free account or something, but they have thousands and thousands, probably not like hundreds of thousands of materials and all of their material properties. And you can actually take those material properties and actually import them into SolidWorks, either by just creating a new material, or I think there's also a way you can download like a preset. So let's say you do that and you put your material for your gray cast iron. Let's say it's a really, I don't know, unique type of gray cast iron. And so this is the thing, if you don't really know, if actually let me actually leave that there. If you're not familiar with failure theories, you're going to say, well, von Mises, I like von Mises, I use it all the time. Well, obviously the failure theory should be von Mises. Well, no, in this case, yeah, like Kevin was saying, it's because it's brittle, you know, you can't, von Mises is not going to probably be an accurate way to model that. You probably want more Coulomb or or maximum normal stress theory. So that is definitely something to look for, especially when you're using materials that are not defaults. Um, okay, so here's that. Let me scroll down here. Any questions or anything about that? Okay. Okay, so here's some stress. Another thing, stress concentrations. This is a big one. So when you have a sharp corner like this, what'll end up happening is you'll end up getting what's called the stress concentration. So you have an artificially high stress in this region. And pretty much the finer you make the mesh, obviously because the elements keep getting smaller and smaller and smaller, this stress in the corner here will actually shoot up to infinity, which is not really accurate, but because theoretically the force is the same. If you remember, stress equals force over area. So technically the force is the same. The area now with the smaller and smaller elements, this area is actually going, going to zero or going, it's getting smaller and smaller. So you're gonna end up making the stress pretty much infinity. So most parts you don't want to have a sharp corner like that. So that's why a lot of times you'll see fillets and stuff like that to relieve that. Here is a actual sample. Playing the carbon steel for this one probably was not the best thing. So if you cannot see the mesh, I truly apologize. If you can kind of see the lines, let me know if anybody cannot see the mesh. It'd be probably better if I did another one, but it looked much better here than it did once I generated the mesh. But that's pretty much this is like a standard mesh size for a part like this. That's kind of what the mesh looks like. And again, these are tetrahedral elements. Okay, so from there, if you run a study, this is kind of again what you're looking at. Um, Again, this is the same exact study from before. This one is obviously without that fillet. It's just a sharp edge. So you look at our max stress here. Max stress is about, let me see if I can zoom in here a little bit. Max stress is about 110 megapascals. Um, for the one with the fillet, with the same mesh size, you're at about 101. So there's not a huge difference here. Again, it is still noticeable. But then watch when I go to a much finer mesh. Let me try to really zoom in here. See, that's a much, much finer mesh. You can see how many elements are across there. So when I go to a much finer mesh there, beat on here, now we just went up to 139. And when we do the finer mesh for this one, which looks something like that, you end up with a von Mises of 108. So 108 from 101, this didn't change that much. It went up by about 7. From this one, though, it went up by, what is it? Like about 30. Um, and what will end up happening is the more fine you make the mesh here, this is going to keep going up and up and up and up. So you'll have a difference of when you deal with your stress versus your element size, as your element size kind of gets smaller. So typically, if you have a graph, let me try to sketch that. I'm almost done, I promise. So when we go here, and if you have so if you say this is, let's see here. Let's say this is stress. Say this is stress. This is element size. I'll call this, I don't know. Let's call this whatever. This is going to be the size. Let's call it size. So what will end up happening is as the element size gets smaller, what will end up happening is it should plateau out. And obviously, the finer you make it, eventually, it's not going to change that much. It's going to change less and less. That's if you have a situation like this. If you have a situation more like this, you have what'll end up happening is you make the what is it called? Am I doing this right? No. I think I actually drew that graph wrong. The size, as the size gets smaller, Yeah, I think I actually drew. Yeah, I actually drew that graph wrong. So ignore that. But pretty much what will happen is the stress will end up going up into infinity like that. Um, so what will end up happening, the smaller you make the mesh, it's going to keep going up and up and up and up until you have this. Now you almost have an infinite stress, which is obviously not accurate. Where something like this, it will actually, um, the stress will actually, do something. It'll actually plateau out eventually, if that kind of makes sense. And that's pretty much, I think that's kind of all I have. But any questions about anything? Kevin's asked like a couple questions. Somebody else needs to, compete with Kevin.
I don't know enough yet to ask good
You're
questions.
good. Yeah, I
So
know that. You're good. I know that's definitely a. I know it's a lot of information. Definitely because there's definitely a lot to go over. Again, that's why everything is recorded. Is there anything that didn't make sense? Maybe that's a better question versus if you have a question. Is anything that didn't make sense and for me to go over again, maybe?
everything was great for me. I just took strength of materials this past spring. So
Okay, so yeah, you probably have an idea of, so a lot of the stuff was probably reviewed. Probably the FEA part was probably the new part, but the, stress, strain, that stuff was probably remember that quite a bit. And then, so yeah, let's see if there's anything else. I think I covered, I would say this is a pretty good overview, um, of pretty much of linear study or linear static studies in SolidWorks. Again, next session, I plan to actually really jump into SolidWorks and actually start showing how to set these things up and kind of what some of the pitfalls are when you're dealing with fixtures and loads and stuff like that. Um, but yeah, so yeah, let me go ahead. If there's no questions or anything, does anybody have any questions before I stop recording? Okay, so let me go. I think that's a good place to stop recording. Okay.